So let's look at some of the mechanisms that have been proposed for MJOs, their genesis and propagation. Obviously, when we say mechanisms, there are multiple because there is no one unique accepted theory that explains all of them. People look at various data, various features, and then build theories which explain sometimes specific cases, and then other people use different data and then come up with different mechanisms. But starting with the ocean SST budget, if you will, mixed layer heat budget, we looked at this in chapter 2 in terms of the contributions to the SST here, in terms of the diurnal heating, the entrainment and evaporation. So entrainment, if you remember, is when the turbulent kinetic energy at the surface is trying to deepen the mixed layer, which is the turbulent well mixed layer, which means it will then entrain waters from below, so that takes energy. And evaporation can cool the surface and create these convective plumes, which can also create entrainment and deepening of the mixed layer, typically cooling the surface unless there is a temperature inversion which can warm the temperature, which happens in some occasions in the regions with freshwater forcing, like the Bay of Bengal, for example. And this is the rain forcing. So talking about freshwater forcing over the western equatorial Pacific, we have tons of rain throughout the year because there is a equatorial convection, and then there is the northward southward propagating ITCZ SPCZ parts. So rainfall also has a contribution when you look at sea surface salinities and temperatures. Okay, so ocean and the surface heat exchanges with the processes we talked about, like the Vichy mechanism, wind-induced surface heat exchange, are considered very important for Madden-Julian oscillation. So all the theories that are proposed, which we won't go into details but look at a table in the end, depend on this energy exchange with the ocean, moisture loading and waves. And there are debates about whether the moisture loading is happening near the surface with friction, frictional convergence, or it's happening in the free troposphere, and so on and so forth. But nonetheless, all of them require these some key elements for MJOs. But the instability generation is well observed in the Toga core data that we looked at also before in chapter 2. So this is looking at synoptic data for a few weeks from a couple of months from the 1.8 south, 156 degree east, so basically in the deep tropical western Pacific. And the daily time temperature SSTs appear fairly smooth, but if you look at the hourly time series of SST, you can see that there are spikes that are order 1, sometimes even 2 degrees, reaching as high as 32 and over. So if the atmosphere is able to quickly respond to these hourly SSTs, obviously that's going to be important to observe as well. And the wind speeds, if you look at the 200 hectopascal and 850 hectopascal, there are times when they are completely different, with the surface wind speeds being very weak and the upper level winds being fairly strong, and sometimes they are both fairly weak, and sometimes they are both fairly strong, as you can see here on these daily and weekly time scales. Okay, so this says that the relation between the warming phase here, going from about 29 into 30 and so on, is associated with weak surface winds and strong upper level winds. And as the cooling happens here, you have wind speeds in phase and picking up from near the surface and weakening somewhat in the upper atmosphere. In fact, surface winds are stronger, and then you again get into the warming phase and so on. So there is a coherent variability between mixed layer of the ocean, processes in the ocean that determine sea surface temperatures, processes in the atmosphere, including the vertical shear and the temperature differences as well. So the 200 hectopascal temperature anomaly also shows that sometimes it is negative compared to the surface, and sometimes it is positive. So this corresponds to when convection is picking up the energy from the surface, moisture loading, convergence, and then deep convection is basically wiping out the instability like the convective available potential energy and creating deep convection all the way to the upper troposphere. And when the surface and the upper level are disconnected, when the surface is building up the instability, and so on. So this is the difference of the 200 hectopascal temperature anomaly and SST anomaly. So you can see where the atmosphere is stable and where it is unstable. So obviously there is a warming phase, buildup of convection, what we call the perturbed conditions when we looked at the fluxes in chapter 2 as a table as well. So that difference is an indication of the buildup of moist static energy instability. So if you have high moist static energy at the surface compared to the upper atmosphere, then you are creating instabilities which can drive convection. So corresponding to that, you have precipitations and cloud amounts. Okay, so there is the precipitation and those are the cloud amounts. And this is the surface to 3 kilometer column water vapor. Again, warming phase builds up the moisture which is associated with building up CAPE, and then the 200 hectopascal volume mixing ratio. When the convection happens and rain occurs, the upper atmosphere obviously gets dried out, and when it is in the convective phase or the building phase, then it loads up the upper atmosphere as well. So this gives you a sense that there are coherent processes happening at the surface to the top that are responsible for triggering convection. Okay, so this is just showing again latent and sensible heats corresponding to those data we saw before. Obviously high latent heat flux loss from the surface would create SST cooling. Low that will warm the atmosphere. Moisture loading in the atmosphere goes up, but it's a loss from the surface. When the latent heat fluxes are low and wind speeds are low, SSTs can warm. Associated with the cloudiness and the convection, the downward shortwave flux also varies, and you can see the various timescales at which the radiation flux reaching the surface also varies. This is the net long wave surface flux, which is much larger than the sensible heat flux, but this is the net surface radiation. So you can see where it's negative and where it gets close to zero in terms of a balance between the radiative cooling and shortwave heating. Okay, so let's look at the composite upper and lower tropospheric humidity buildup in the next podcast. But the main idea of looking at this data is that there is coherent processes. There are coherent processes happening at the surface. Buildup of ocean SST ahead of the convection, instability triggering the convection, removing the instability, mixing up the air column, and then next phase of reorganizing the SSTs and continuing the process. So convection has to keep moving eastward, and we talked about this before, where we looked at the heating and convergence into the heating with easterly anomalies on the eastern side, westerly anomalies on the western side, and we talked about the asymmetry because this is going to create convergence and warming ahead of it. This one is going to create Ekman upwelling and cooling. So we said in the tropics it's very hard to imagine a convection that is being stationary, that basic processes associated with the anomalous winds of the convective heating end up creating this eastward propagation, but this is specifically about the MJO timescale. Okay.